There are a total number of num courses you have to take, labeled from 0 to num courses minus 1. You are given an array of prerequisites where prerequisites I equals A of I, B of I indicates that you must take course B of I first if you want to take course A of I. For example, the pair 0, 1 indicates that to take course 0, you have to first take course 1. Return true if you can finish all of the courses, otherwise return false. So at first glance, it might not seem intuitive what would be a situation where we're not able to take all of the classes. But if we look at example 2, we're given exactly that. We're given 0 needs to be taken before we can take class 1, and then we have to take class 1 before we can take class 0. So for this example, we have a paradox. So we return false. So let's visualize this first before we move on to more complex examples. For our second example, we had 1, 0. And then we had 0, 1. So for our first prerequisite, we had to take course 0 before we can take course 1. So that's going to look like 0, arrow, 1. We need to take course 0 before we can take course 1. And in our second prerequisite, we have to take 1 before we can take 0. So we're just going to draw an arrow this way. And we can see this is how we get our paradox. In computer science, we call these nodes and these arrows a graph. And when we see this sort of paradox where one node leads to another and then back to itself, we call this a cycle. So for this problem, all we have to do is see if we can detect cycles. And if we detect a cycle within a graph, we can return false. Otherwise, return true. So let's see a couple more examples and let's see if we can figure out a way to detect cycles in graphs. So there are actually a few ways of doing this, but for today, I'm going to be going over something called Kahn's algorithm. So what is Kahn's algorithm? Essentially, we look at the graph and we say, all right, what nodes do not have incoming edges? So we can observe here that we have no incoming edges here and no incoming edges here. Let's add these to a queue. Our queue right now is 0 and 4. It really doesn't matter which way we took this. We can do it either way. And we say, whatever node that's next in the queue, we are going to remove it from the graph. So we're going to say, wipe this one away, as well as all of its edges. So we got rid of the 0, and we got rid of the 4. Now that we've gotten rid of this, add all of the nodes that have no incoming edges to the queue. So 5 and 3, and continue this process until we have no nodes left. So we could say next, we have the 4, let's get rid of that. Get rid of the 4 from this graph. Can we add any more elements to our queue? No, we can't because this 2 still has incoming edges. So then we just go to the next part of our queue. We start with the 5, get rid of the 5, remove this from the graph, and we add any nodes that do not have incoming edges. There's nothing more we can add, so we're just going to say, go to the next element. Remove the 3, keep going, add the 1, remove the next from our queue, remove from the graph, and then add whatever element's left that has no incoming edges, put it into our queue, take the next from our queue, remove it and all of its edges. If we have no more in our queue and no more in our graph, then we know that we have no cycles. Now let's do this again, except let's add an edge from 2 to 3. So we can see here if we travel from 3 to 1, then 1 to 2, then 2 to 3, we're going to have a cycle here. So let's see what this looks like with our algorithm. So let's make our queue, and let's add things to the queue. No incoming edges here or here. So we're going to add our 0 and our 4 again. We're going to remove the first element from our queue, and we're going to remove that element from our graph. So remove the 0. Can we add any more elements? Yes, we can. We can add the 5, and we can't add the 3 because we have an incoming edge now. 5. Let's remove the next from our queue. So that 4. Let's remove it from the graph. Get rid of this and all of its edges. And we say, can we add any more nodes to our queue? No, we can't. The only node that has incoming edges is the 5. Let's remove the next from our queue. So let's get rid of that 5 and all of its incoming edges. And now we're left with only this. All of these nodes have incoming edges. We can't add anything to our queue, and we can't remove anything from the graph. In this situation, we know we have a cycle. So in this case, we'll return false. So let's start coding up our solution. First, let's figure out a way to represent our graph and the number of edges going into nodes. And we're going to use this for that. So there are a few ways of representing a graph. In our solution, we're just going to use an adjacency list, which is just a dictionary. And for each key value pair, we're going to have a node. So a node that points to a list of other nodes. And this list is going to be our neighbors. The incoming list is just going to tell us how many edges are going to our node. We're going to be using a queue later, so just queue equals some empty list. But first, let's initialize our graph in our incoming dictionary. So let's iterate over our input, so this prerequisites, and we're going to say adjacency list source, and it's getting a new neighbor, so append destination. And we're going to be updating our incoming list, so incoming, whatever our destination is, tst, and then add 1 because it's getting a new edge toward it. So now let's start looking through our graph and say, are there any nodes that don't have any incoming edges? And let's add them to our queue. Let's actually rename this. Let's call this no incoming queue. Let's iterate over each one of our courses. And if any of our nodes have no incoming edges, we append that node to our queue. All right, so let's finally get to Kahn's algorithm. In our picture example, we were removing nodes and edges until we either had no nodes left. Instead, we're going to counts, so we don't actually remove anything from the graph. Count equals 0. While we still have nodes in our queue, we're going to remove the first element from our queue. Let's call it source. Because we're visiting a node, we're just going to increment the count. And we're going to get all neighbors of our source node. And we're going to decrement all of our neighbors, which is just another way of saying we are removing the edges in the graph. So after we remove all the edges, then we want to check to see if there are any more nodes that we can add to our queue. We're only affecting the neighbors of our source node. So every time we decrement, we're just going to check our neighbors to see if we've removed all of their incoming edges. So we say, if there are no more edges in our destination node, then we append our destination node to our no incoming queue. So we continue in this algorithm until there's nothing else in the queue. So then finally, we just check to see if the number of nodes that we added to this queue equals the number of courses that we're expected to have. If this is the case, it means that we've removed all nodes from our graph. So we return true. If not, it means we found a cycle, we return false. So let's see if this runs. Cool, let's see if it works. And there we go. Link for the code will be in the description. Like, subscribe, and join our Discord for some more. See you in the next one.